organic chemistry now. So let's start with benzene and its derivatives. Benzene are known as arenes. What do you mean by arenes? Arenes are aromatic compounds. Aromatic compounds are those compounds which have a specific smell or a specific aroma, is why we call them aromatic. So benzene is an aromatic compound with a distinct specific smell. Benzene ring is the simplest aromatic compound. So benzene ring is the simplest aromatic compound. And the formula for benzene is C6H6. So this right here is a formula for benzene. The old structure of benzene was proposed to be as 6 carbons arranged in a ring with alternate double bonds like this. So let me draw the structure of benzene. So this right here was the old structure of benzene, which was proposed to be as a ring, a cyclohexane kind of ring. Yes, a hexagonal ring with alternate double bonds. So each double bond, each alternate bond will be a double bond. And right here you have a hydrogen, a hydrogen, a hydrogen, a hydrogen, a hydrogen here, and a hydrogen here. Do you see you have 6 carbons and 6 hydrogens? Now let's look at each carbon. Let's look at this carbon. This carbon right here is making 1, 2, 3 sigma bonds. So this is making 3 sigma bonds and it has 0 lone pairs. Steric number is 3. Hybridization is sp2. So each carbon in benzene is sp2 hybridized. So each carbon in the structure of benzene is sp2 hybridized. Why? Because you can see the hybridization comes out to be sp2, right? Now each carbon is sp2 hybridized and attached to 2 other carbons in a hexagonal ring. So it is attached to 2 carbons in a hexagonal ring, as you can see right here. So we have a hexagonal ring. Right here we have a carbon, and each carbon has 2 neighboring carbons in the hexagonal ring. And this right here is your structure of benzene. Now benzene is a liquid at RTP. So benzene is a liquid at RTP. And like I told you, each carbon is sp2 hybridized. So if it is sp2 hybridized, let's see the excited state of carbon. So you know you have the nucleus, then you have the 1s, you have the 2s, and then you have the 2p. Right here we have the 1s2, 2s1, and 2p, 1, 2, and 3. And this undergoes which type of hybridization? sp2. So 1s hybridizes with 2 p's, giving you one unhybridized p orbital. Can I call this the unhybridized p orbital? So this right here is the unhybridized p orbital, right? So you have sp2 hybridization, then you have one unhybridized p orbital. So you have each carbon attached to 2 neighboring carbons in a hexagonal ring. All carbons are sp2 hybridized, like I told you, and it is what it is. One orbital will be unhybridized. Why will it be unhybridized? Because sp2 hybridization means that 1s mixes with 2 p's. So the third p is unhybridized p orbital. So this right here is the excited state of benzene. Now, these p orbitals, which are unhybridized, the unhybridized p orbitals, they overlap to give you a pi bond. That's what used to happen with alkenes also. So the unhybridized p orbital, they overlap. So the unhybridized p orbitals, they overlap to give a pi bond. So they overlap to give what? A pi bond. So they overlap to form a pi bond. Now, what is a pi bond? We know the pi bond is a delocalized bond, right? For example, if you remember, now in benzene, it's delocalized. Like if you remember in alkenes, this was a double bond, it was a pi bond. And I told you that the pi bond can be shown as what? an electron cloud above and below the nuclei. Write this. Yeah. So this was a pi bond. Likewise here, can I say that this will be an electron cloud above and below the hexagonal ring? What happened? Do that. In benzene, we have one unhybridized p orbital for each carbon. And that unhybridized p orbital overlaps to form what? It overlaps to give you a pi bond. And this pi bond will be what? An electron cloud above and below the ring. Like if you remember, pi bond used to be an electron cloud above and below the nuclei. Do you remember this? We could represent the pi bond like this. Yeah. The same way, the pi bond can also be represented as a cloud above and below the hexagonal ring. So that is the pi bond here. Now each carbon, now you see you have 6 carbons here. So each carbon in benzene has one unhybridized p orbital. So it has one unhybridized p orbital. So we have a total of how many unhybridized p orbitals? So we have total 6 electrons that are unhybridized. Yeah, one for each carbon. So you have a total of 6. And these 6, they are uniformly distributed. So they are uniformly distributed around the carbon atoms. Let's see how. So they're uniformly distributed around the carbon atoms like this. So you will have the 6 carbon atoms arranged in a ring. And right here in the middle, we will have what we call this as a pi ring. So this pi ring is a delocalized ring made up of 6 electrons. Around each carbon, you see it is uniformly distributed. And you have a hydrogen here, a hydrogen here, a hydrogen here, hydrogen here, hydrogen here, and a hydrogen here. And each carbon that you have here is sp2 hybridized. So each carbon is sp2 hybridized. Clear? So you have 6 carbons, sp2 hybridized. Each of them has one unhybridized p electron, which are uniformly distributed to form a pi ring in the middle. And this right here is the structure of benzene. Now let's say if they ask you to describe the structure and bonding of benzene. So how will we describe the structure? So let's see the structure of benzene. So we know that it has a hexagonal ring, yeah, of 6 carbons. So you have C6H6, that's the formula. All carbons, they lie in the same plane. And why do they lie in the same plane? Because the hybridization is sp2 hybridization. So what is the shape? The shape is planar. So because they are sp2 hybridized, they are planar. And what will be the bond angle? The bond angle will be 120 degrees. Let's see the bonding. So the bonding for benzene would be, they are sp2 hybridized. We know the carbons are sp2 hybridized, right? And you have unhybridized p orbitals which form a pi ring. So the unhybridized p orbitals form a pi ring. So it forms a pi ring in the center around the 6 carbons. Yes? So this right here is your structure and bonding of benzene. Now, let's see another question. Why is the structure of benzene, why is it planar? So we know that it is a planar structure because you have sp2 hybridized carbon atoms. Because you have sp2 hybridization is why the structure is planar. Let's see the next question. What type of orbital overlap do you see between the carbon-carbon bond in benzene and between the carbon-hydrogen bond in benzene? So we know that each carbon is sp2 hybridized. So what will be the overlap here? An sp2 with an sp2. Because this will be sp2 hybridized, this will also be sp2 hybridized. So which orbitals will overlap? The 2 sp2s. And between a carbon and a hydrogen, what will be the orbital overlap? It will be sp2 with the s orbital overlap, because Hydrogen has its electrons in the s orbital. Clear? Then let's see the next question, which is why was the initial structure of benzene refuted? So they rejected this initial structure. This is the initial structure of benzene, right? And this was refuted, and this is now the acceptable structure of benzene. So why was this initial structure refuted? And why is this now the acceptable structure of benzene? So let's see. The initial structure, which is this, was refuted because benzene does not decolorize aqueous bromine. Just like alkenes, we think that this also has a double bond like alkenes. So this should also decolorize bromine, but it does not decolorize aqueous bromine. Therefore, this will be a misrepresentation of the structure of benzene. We think it looks like alkene, it has double bond, should decolorize bromine, but it does not. So it is not acceptable. Other than that, benzene does not react with KMNO4. So it does not react with KMNO4. If you remember, alkenes would get oxidized with cold dilute and with hot concentrated, but this does not. So that's why you can't say that it has double bonds like alkenes. Other than this, each bond length here in benzene between the carbons is 0.139 nanometers. So carbon-carbon bond length in benzene, all carbon-carbon bond lengths, all of these lengths, they are all the same, are all what? 0.139 nanometers. So if the bond lengths, all of these bond lengths are the same, that means the bond strength should be the same, right? So that means the carbon-carbon bond strength, all of them, all carbon-carbon bond strength should be equal because the bond length is equal. But if you have a double bond here and a double bond between these two and a double bond between these two, that's a misrepresentation because you will think these guys are stronger. You think this is stronger. This is stronger. So you would think that three of these with double bonds are stronger and the three single bonded ones are weaker. But that's not true. All of them have equal strength because they all have a bond length of 0.139. So this structure was refuted because it gives you a misrepresentation of the bond strengths. All of these carbon-carbon bonds, despite the single or the double bond, they are all equal strength. So that's why this structure was refuted, because this makes a seem like this, and this should be strong because they're double. And this, and this should be weak because they are single. But that's not true. They all have equal bond strengths because they have equal bond lengths. Is because of these three reasons, this structure was rejected. All right. Now let's see the physical properties of benzene. The first is benzene is a liquid at RTP. So benzene is liquid at RTP. Then benzene is colorless. It's a colorless liquid with a characteristic odor. That's why we call them aromatic, because it has a specific aroma. Then the molecule of benzene is non-polar. And since it is non-polar, it is insoluble in water. So it is insoluble in polar solvents or insoluble in water. And why is it non-polar? Because it only has carbon and hydrogen. So it is non-polar. What is the melting point of benzene? It is 5.5 degrees Celsius. What is the boiling point of benzene? 80.1 to 83.1 degrees Celsius. So these are the properties of benzene. Any questions so far? All right. Now they ask you, why is benzene liquid at RTP? So now let's move on to why benzene is liquid at RTP. Now we know this is non-polar. So which type of intermolecular forces will this have? Temporary dipole, induced dipole forces. So since it has temporary dipole, induced dipole forces, we know the strength of those forces depends on number of electrons. So let's see, why is benzene liquid? Because benzene has 42 electrons. And these 42 electrons are not too less. They are pretty a decent number of electrons. Therefore, benzene has stronger intermolecular forces. So therefore, benzene has stronger intermolecular forces, which are which ones? Induced dipole, temporary dipole forces. Yes, so it has strong induced dipole forces, which allow benzene to be a liquid at RTP. So that allows benzene to be liquid at RTP. Clear? Now, benzene has delocalized pi bond. Is it a good conductor? Now, we saw that right here, benzene had one unhybridized p electron. Do you remember this? And that was making the pi bond, which we refuted, but we said that this was the pi ring. Yes? Rather than having the pi bonds, we should have the pi ring. So if you have a pi ring, we know it is a delocalized pi ring. So should it be a good conductor? Because for conductivity, we need delocalized electrons. But despite having a pi ring, this is not a good conductor. Why? Because it is non-polar. And since it's non-polar, it has poor conductivity. So benzene, despite having a pi ring of delocalized electrons, it is a poor conductor because it is non-polar. Is this